Now, a lot of functions we can use and solve generally. Let's see here. But there's going to be some, especially when we start talking about exponential functions, that are going to be a little bit harder to solve. So if I said 2 to the x equals 4, we want to know what power of 2 would make this statement true. So power of 2 would make 2 to the 2 equal 4. 2, because 2 squared is 4, yes? And if I said 8, 2 to the x equals 8, x is equal to 3. 2 to the x equals 10, x would be because 3 is 8, and if we multiply 3 by 2, we get 16. 8 times 2 is 16, yes? So that means there's not a whole number answer that we can put 2 to get 10. And this is where logarithmic functions really come in handy, because we can start solving these kind of exponential functions where x is not a whole number. Where x is not a value, we can just use the calculator to guess and check. And that's where we get logarithmic functions, or kind of part of it. And another part is dealing with big multiplications. Now let b and y be positive real numbers with b not equal to 1. The logarithmic of y with base b is denoted by log base b of y and is defined as this here. So what we can say is that log base b of y is equal to x if and only if b to the x is equal to y. And we're able to rewrite these exponential and logarithmic equations in this way. We can change between these two forms. This is what I was looking for. The expression log base b of y is read as log base b of y. Our base x and what we have it equal to. And they'll change in this way here. So we can go from exponential to logarithmic or logarithmic to exponential. So let's try rewriting some of these equations. So the first one we have is log base 2 of 16 is equal to 4. So if I want to rewrite this as log or exponential, so our base is 2. I can rewrite it out here. Log base b of y equals x gets rewritten as b to the x is equal to y. So we're going to have 2 to the what? Because b to the x. So what is our x in this case? X corresponds to the 4. It's what it's equal to. So 2 to the 4th is equal to 16. Any questions on this here? So we good with this here so far? Yes? Plug 2 to the 4th into your calculator. See what you get. So what do we get when we take 2 to the 4th? So this here is a true statement, yes? So if they give us straight numbers all the way through, we can just plug it in to double check our work. Because 2 to the 4th is 16. We do have a true statement. Any questions on this here? So let's look at the next one here. Log base 4 of 1 is equal to 0. So how can we write this? 4 to the 0 equals 1. And if we want to double check it, we can type 4 to the 0 into a calculator, and it's 1. Anything to the 0 power is 1. Any questions on this here? So let's look at some more. Log base 12 of 12 is equal to 1. So 12 to the 1 is equal to 12. Well, anything to the first power is just what the number itself, yes? So 12 to the first is still 12, so it works. What about the next one? Is equal to? Now, according to our laws of negative exponents, if we were really to work with this here, well, to make the exponent positive, we have to move it from the denominator to the numerator or numerator to the denominator. And we also learned if we have fractions, we can flip them, which would just give us 4. So when we just have numbers, it's kind of nice because we can be able to check to make sure we got the correct result. Mm-hmm. 216. And I think y'all are starting to see the pattern. What? 216, yes. Thank you. I need to finish writing before I start thinking. So I think y'all are starting to see the pattern, yes? We take the base and put it what it's equal to, and put the number inside the logarithm outside. So when we look at log base 7 of 1 equals 0, we have what? 7 to the 0 is equal to 1. TV equals. Yep. I put parentheses around the 1/5 when we have these fractions just so we know that the exponent that we're going to apply to it goes to the numerator and denominator. Because 1/5 isn't bad, it's understood that it would just go with the 5. 1's not going to change anything. But if we had 2/5 or 3/5, it's good to know that it's attached to both. Any questions on this here? We can also go the other way around. Because we aren't able to just go from logarithmic to exponential, but we can also go from exponential to logarithmic. So if I look at 5 squared equals 25, well, the first thing I need to write is we'd have log base 5 of what? 25 is equal to 2. So we're just going in the other direction. So we drop, so our base would be 5. Move the 25 from the other side of the equal sign is equal to 2. Any questions? Huh? Yeah. So what would be the answer for the next one? Yes. Any questions on any of this here so far? Now this here is actually quite helpful. Bless you. Bless you. Because the problem we started out with, that we kind of got stuck with at the beginning of class, was 2 to the x equals 10, yes? Let's rewrite it as a logarithmic. What would this be? 2 of, bless you, is equal to there's ways to actually calculate log base 2 of 10. So with these logarithmic functions, it's given me a way where this here, bless you, it'd be very difficult or very challenging to try to figure out what value of x would make this true. But here, log base 2 of 10, I now have a way to calculate the value of x. That's why these are nice. This is one reason that these are nice to have. So let's look at two more, at least. So 8 to the 2/3 is equal to 4 would be log base 8 of is equal to log base 8 of 4 is equal to 2/3. How about the next one? Almost. Bless you. 1/2/6. Because what goes inside is always from the other side of the equal sign. Now, this will be a little confusing for at this point, but once we delve into more of the properties of logarithms, there's a certain property that we can apply, and once we apply that and we've gotten that, it's going to make why this work makes so much more sense. All right, let's work from the top down. Yes. And then the next one would be of base 20 of yes. C. And last but not least, any questions on any of these here? So any questions on anything we've done so far before we start evaluating these logs? Now, the way that we can go about evaluating these are in one of two fashions. And the main way, especially what the book is going to say, is that we're going to set this equal to x. We're going to set this equal to x and use exponentials to solve this. So, if I rewrote this as an exponential, we would have what? 4 to the is equal to so 4 to what power is 64? It'd be 3. Because if we put 4 cubed into the calculator, we would get 3. Because really what we're saying, 4 to the x, well, 64 is 4 to the third, so x is equal to 3. Any questions on this here so far? Let's rewrite b, because we're starting off with log base 5 of 0.2 is equal to x. Now, 0.2, how can we rewrite that as a fraction? What is 0.2 as a fraction? It is 1/5, yes? Now, I rewrote it as a fraction because it's a little bit easier to work with, a little bit easier to see. Exactly, yes. Now, kind of like I did on the other one here, it's not so much that I expressively said it, but we rewrote 64 as 4 to the power, so we can match the exponents up. Well, I can get this to be the same on both sides, because I can move the 5 from the denominator to the numerator. But if I do that, the exponent becomes negative. Still, it tells us x is equal to . So mainly the new thing that we're covering or doing today is not so much the solving part, because rewriting exponents, manipulating the numbers, we've done that before in some form or fashion, yes? Because we've messed with negative exponents. The new step is going from here to here or here to here, and because that's the new step that we learned, is really being able to rewrite these exponentials as, or logarithmics as exponentials, or exponentials as logarithmics. Do we have a log function or a log button on the calculator?
Yes.
So what would be log of 64 if we typed it in? So we can hit the log 64, and we get 4 or 3, yes? No? Wait, does it have a 4 down there for a base? No. The log button right there is in base 10. So what that is saying and what we just typed in would be log base 10 of 64 is equal to x. Or we're saying 10 to what power is 64. Well, that's not what we wanted, correct? No. So there's going to be a process that we can go through, and we'll go through change of base. How we can change it from base 4 to base 10 and get it to work. Or, because I knew we'd have more, in the calculator, hit math, and either scroll down or scroll up, either way. Because unfortunately the TI-30XS doesn't have this feature. And you should see something called log base, yes? So go on and type C in and see what we get, or D in. So we can go math, and then we scroll down to log base. So log base 36 of 6 is 1/2, yes? So if I rewrote this as an exponential, we'd have 36 to the x is equal to 6, yes? Well, what would I have to do to 36 to get it to be 6? Well, 6 squared is, so this here really is 6 squared. 36 is 6 squared, yes? If I want to get 6 to the first, yes? So what times 2 would give me 1? So it would be, as we found on the calculator, x is 1/2. Any other questions on this so far? Any questions over anything we've done thus far on any of this here? Okay. I want to look back at this here. Now, this might be a little bit early. We might cover this again later. But one of the things I want to talk about with this function here is kind of the steps that I just showed you. Because I do know 36 is 6 squared, yes? And over here we just have 6 to the first. So I'm able to make the bases be the same, yes? Now over here, 6 squared to the x is 6 to the 2x, yes? Is equal to 6 to the first. So are the bases the exact same? Well, yes, we have 6 and 6. Yeah, no, the exponents are different, yes? So the bases are the same because we have 6 and 6. So the only thing that's different is the exponents, yes? We call this 1 to 1. 1 to 1, one base to one base. They are the exact same, yes? So if these here are going to be equal, are going to be the same, what has to be the same? The exponent. So we can say 2x is equal to 1. This is the 1 to 1 property. And we'll get probably more into this later on in the chapter and cover this again. But if I want to find the value of x, I would divide both sides by 2, which would tell me x is equal to 1/2. And that's essentially what we've been using up to this point, especially with the first one, where we had 4 to the x equals 4 to the third, x equals 3. We're using 1 to 1 property. So any questions on this here? So let's do the next one. We could plug this one into the calculator too. So this here would be -3 because we can go log base 1/5 of 125 and hit enter, and it'll give us our answer. Because if we wrote this out, it would be 1/5 to the x is equal to 125. If I want to solve this out by hand, I want to get 5s up top, so it's a little bit easier to work with. I don't have fractions. And 125 is 5 to the third. So what we really have is 5 to the negative x is equal to 5 to the third. So really we're saying negative x is equal to 3, or x is equal to -3. Trying to make sense how this process kind of works. And it works out nicely, especially for what we're doing here, because the bases are the same. The bases work out to be the same number. So what would these be here? So the first one would be 4. One half. And these here, we can type these in. Because especially if we have a graphing calculator that'll do it for us, might as well utilize it. Yeah. B18. And we could work through these in time. Any questions on any of these here? It's kind of nice when the calculator works for us, yes? Now, the other type that we have is natural logarithms. You're not going to have to rewrite these, at least for this homework assignment tonight, or the one you get from today, is this here. ln is the natural log. I have no idea why they wrote it ln instead of nl, because natural log, it should, normally we would put the first letter, or first initial first, but they decided ln. ln of x is equal to y, is the same as e to the y is equal to x. Now, it's the same type property what we use for logarithms. We take the base, put it to what it's equal to, and what's inside the log goes on the outside, yes? But with natural logs, the base is understood to be e. The base is understood to be e. So we don't normally write it. So when we talk about natural logs, ln of x equals y is enough. We don't actually have to write its base. The same thing is true with logarithms if the base is 10. If the base is 10, we just write log. We don't write log base 10. So if I wanted to rewrite this here, ln of 6 equals x, we would rewrite this as what? E to the x is equal to 6. E to the x is equal to 6. And it's the same type process for what we did with logarithms. Now we just have natural logs, and we kind of have this understood base of e. ln of 5a is equal to b. E to the, so we wouldn't use y, we would, b is equal to 5a. What's inside? E to the b is equal to 5a. Any question on either one of these here? So let's look at the next two. ln of 42 is equal to b. E to the b is equal to 42. E to the 6 is equal to b. Now these here are a little bit harder to check, so I use variables for this here, because e is an irrational number. It's a non-repeating, non-terminating decimal, yes? So I really can't include the whole number for z, because we could find out what e to the 6 is, but it would be a non-repeating, non-terminating decimal. We couldn't get the whole thing. Any questions on this here? E to the 4 to the y. E to the e is equal to 3a. Yeah. Now I threw that in there just to see if y'all could keep it straight. So this time we're going the other direction. We're using our ln's. ln of x is equal to 9. We don't have to write the base, because we could say natural log base e of x is equal to 9. But because the natural log's base of e is understood to be that base, we don't have to rewrite it. So we just can say ln of x is equal to 9. any question with either one of these. Last two. Yes. Any questions on any of these here? Well, I see we have two more, but do we feel comfortable for the most part with these here? Yes? All right, last thing we're going to look at. Evaluate log of 8 and natural log of 3 using a calculator. Round your answer to 3 places. If I want to find out what log of 8 is, I'm going to hit log of 8. And since it doesn't have a base, we can just use base 10. So we can just use the log button, 8, and we get to 0.9030. So since it wants 3 decimal places, and the 4th place is a 0, bless you, we would use 0.903. And this would be what log of 8 is equal to. Now, if we take the natural log of 0.3, we get what?
If I put 124, that's actually just the rounding. 1204, but this is 1203. 1.2. I hate math. 1.20. I rounded already. My brain is stop working. Just call me Fred.
Negative 0.523. Five, 2, 3, I think is what y'all got, with it rounded at the 3rd spot.
Did I not do something? Yeah, it is my calculator.
Maybe I'm just blind and can't see.
All right, let me double check. Yep, I don't know. Second one is ln, so it's negative 1.204 would be ln. So it looks like log of 0.3 would be our negative 0.5. All right.
What was it? I'm so sorry. I was
You're good? Negative 1.204. So if we took log of 98, what would we get? 1.991. As we know, the base is 10, yes? Well, 10 squared is 100, yes? So we would expect this number to be close to 2 because we're trying to see what power of 10 would give us 98. How about log of 9.8? 0.991. Well, to go from 98 to 9.8, we're just dividing it by 10. We're moving the decimal place. How about ln of 7.84? So for most of these here, we can plug them in. And that's it. That is all we have for today.